So, welcome friends. So, today we initiate a new chapter after the chapter on capacitors, and today we'll talk about what is generally called current electricity. Electric current, which is known as vidyut or kaharba in Arabic and barq in Urdu and Persian. This has been there under observation of the human beings for a very, very long time, because there is a natural phenomenon of lightning where when the clouds they rub, then a potential is created over there, and the potential of the earth being a very large sphere, if you take that potential to be equal to zero, then there is a big potential difference which is created, and the charge leaks from the clouds to the earth and thereby creates what is known as a lightning. So this is one of the natural phenomena which has been observed since time immemorial, and there is a neural network where we know that the signals, they are transferred from this portion and this portion to all the parts of the body of all animate objects, and therefore there is a proper reaction, a proper training, etc., etc. So I'm not going into the details of that. What I'm going to talk to you about initially is the steady electric currents. An electric current which is steady, that means it doesn't change, which is created by the transfer of charge from a level of potential to another level of potential. Okay. And if Q charge is transferred in time t, positive Q, from levels of higher potential to levels of lower potential, like in the case of water flowing from higher levels to lower levels. Okay. So that analogy is there. So I can simply write that the electric current, which has a symbol capital I, small I, etc., is equal to the charge Q divided by the time t, and it is expressed in what is called amperes. The unit of electric current is amperes. And from here I can just say that this is dq dt, rate of change of charge with time, and the unit is ampere, as shown over here. Ampere is coulombs per second, but ampere is a fundamental unit. Coulomb is not. A fundamental unit, just like meter, kilogram, second, and the temperature Kelvin. Similarly ampere, and it will be defined later on when we talk about the forces that the two wires they experience later on, a few lectures away from it. So suppose there is a flow of charges from left to right, and there is a surface through which the charges are flowing, both positive and negative charges. The flow is shown as Q plus per second and Q minus per second. So this Q, this will result in a net flow in this direction from left to right, and that will be Q is equal to Q plus minus Q minus. Okay. As a result thereof, the electric current which flows through the system, and that is known as I, and in the system of units that we talk about it is amperes. Okay. So what I can express all these things is as follows. In the systems approach that we have been doing, that the charge is proportional, charge passing is proportional to the time t. Therefore Q is equal to a constant times t, and this constant of the system is called electric current. So if I plot like I have been doing several times, Q versus t, then there will be a graph which is a straight line and the slope of it will be equal to r. Okay. Now let's talk about certain things. For example, conductors. Conductors are, when I say conductors, we are talking about good conductors, which are not insulators, which are not semiconductors, etc. Normally metals. And one of the properties which says one conductor from another conductor differentiates between conductors is called conductivity. Okay. We'll talk about that later. And that way we see that among the elemental conductors, silver is one of the best conductors. Next comes copper. But silver is costly and copper is cheaper and good, malleable also. Okay. And therefore we can draw thick and thin wires out of it, of uniform cross section, etc., etc. And I am just telling you about a cylinder made of, say, copper or silver, one of the conductors. And suppose I have these two faces through which a current is passing. If this is plus Q and this is minus Q. Okay. But what will happen? Then I'm just showing that there will be an electric field, but inside the electric field cannot exist, and therefore we say that there will be a potential gradient dV dr. Okay. No problem. So this I have a potential V1 and this I have a potential V2. Absolute values of these potentials, V1 and V2, they are immaterial. What is material is the potential difference, which we normally represent with the capital V. Potential difference, also known as voltage. Okay. This metallic cylindrical wire or cylinder has got a length L and an area of cross section which is we call A. Now if the charges over here are, say, maintained, but I will not talk about charges. If the potential difference is maintained somehow, I will tell you how. These two potentials, this can be positive, this can be negative. This can be positive, a higher value, and this can be positive, a lower value. This can be negative, a lower value, and this can be negative, more negative. But the difference has to be positive V. Then, because this is positive polarity and this is negative polarity, and in the metal, we have plenty of, what did I say? Beforehand, when I was telling you about the conductors, I said these electrons, they sing a song. Avaram, avaram. So these are vagabond kind of electrons which are drifted towards the positive polarity. So what we get is, under the presence of the potential difference, what we get is a drift current. The electrons with negative charge, they move like this. Okay. Hardly there are any positive charges that will move because they are very heavy and they will be blocked by their neighbors. So it happens that the electric current passes like this. Okay. The maintenance of the potential difference between these two phases, which I have just shown over here, V12 is equal to capital V, and here I am just grounding it, earthing it. So this point I have shown to be 0. So this is positive and this is negative, and they are connected by some means from this point back to this point. Okay. Just telling you that these kinds of things exist. And if so, using the supply, the energy supply, we have cells of different kinds, which can be put in the form of a battery, positive, negative, positive, negative, positive, negative, positive, negative. The phase, this positive one is longer in length and negative one is shorter, and sometimes it's thicker also, the line that may go there. This is the symbol of a cell, this is the symbol of a battery, and this is the symbol of a variable potential difference. In fact, what we call, and we'll talk about that, what the cells provide is an EMF. This used to be called electromotive force historically, but there is no force. In those good old days, force and energy there was a confusion. So for centuries, we took it as electromotive force. Should have been electromotive energy. It doesn't matter. So there is a potential difference. And we respect our history. The history has to be respected. The history has not to be rejected. Okay. So therefore, EMF is what we maintain. Now, let's talk about some symbols that will appear in the due course of time when we talk about the circuits. I'm not talking about circuit. So there are some straight lines like this. These are connectors. Now about the connectors, one thing is there, that suppose there is a current which is passing through it. Okay? If the current is passing through this, then every point on the left should be at a higher potential as compared to a lower potential. But we understand that the potential on each and every point on this line is the same. Okay? Because the resistance offered by this line, which we use for representing connecting the things in the circuits, that is negligibly small. Earlier in my good old days, when I encountered this kind of things in my lab in the class 12, then there was used to be copper wires which were wound like this, and they had a jacket, a muffler of cotton thread. Anyway, this is a symbol where two lines, two connectors are crossing each other such a way that they jump each other. Okay? But in electrical circuits, also in the case of electronic circuits, there are certain connections like this. They just cross each other, these lines, but there is nothing like this. This means that they are joined. This simply means that they are not joined. This is separate and this is separate in that representation. Okay. Well, there are some switches they are also included. Switch like this is open, and when I make a connection like this, then the switch is closed. Open switch has infinite resistance and closed switch has zero resistance. I'll tell you what a resistance is a bit away from now. And similarly, this is an open key, and when we insert the key over here, okay, then it is closed. So open, close, switches, etc., etc. And then besides these, we have certain symbols like this. They are the symbols of conductors or resistors. Okay. Like this we go, right? And if they are to be varied, they are to be made variable, then there is a line which is put over there. And similarly this one, okay? And particularly in the old Russian books, the resistors used to be shown like this. So they had a different way. So friends, that way we come to 1826. 1826 there was a study, and that study was made by a German school teacher. His name was Simon Ohms. And this gentleman, Simon Ohms, you have read about it in your class 9, 10th, when this thing was introduced. This gentleman found that the potential difference is proportional to the current. Conversely, the current is proportional to the potential difference. And he found that V is equal to Ri. This is what I am going to take up just now. But you remember it, you know it, where R is called resistance. And the reverse of resistance is called conductance. Ohm was honored by making that unit of resistance as ohm, but the unit of conductance 1 upon ohm. Okay, ohm in Greek, I can have a symbol like this. I showed it to you in one of the lectures. This is a symbol like this, ohm. So 1 upon ohm was given a symbol something like this. Some people thought that this will do, the inverted ohm. Okay. And some people thought that we can write it ohm power minus 1. Until some people thought, what is this we are doing to ohm? And there was some protest from certain Germans and from the family of Ohm. What are you doing to Mr. Ohm? Okay. The great grand old man. Okay. So then a unit was introduced in the name of another German, Siemens, an engineer. So you have companies like Siemens companies all over the world, and we have a company, Siemens India, in which one of my boys, nephews, he worked for substantially long amount of time. Siemens, and the unit is simply that S. Okay, so Siemens is the opposite of that. I'll just tell you about Ohm's law and beyond. So the beautiful, lovely Ohm's law, which was given in 1826 probably by a German school teacher by the name of Simon Ohms. You can check that. Okay, maybe I'm right, maybe I'm not so right. Okay. This German school teacher, he studied conductors, which we also call resistors, which is a symbol over here, and he made a circuit. Circuit means you start from some point and end up at the same point. Of course, the switch is made. Once the switch is made, then this cell or battery or whatever source of EMF, as I told you, electromotive force, the potential is variable. We can fix the potential, change the value of V. So we find, and of course, Ohm used a meter for measuring the potential difference and a meter to measure the current. Okay, we'll talk about that later on. So, in a nutshell, what is there, that this measured value, which is a dependent variable, depends upon the independent variable. These two are variables. So I is proportional to V, and like all cases of proportionality, I is equal to a constant times V. This constant is represented by the capital letter G, and it is called conductance. As I told you, the unit is Siemens, S, but earlier it used to be Ohm inverse, MHO, Mho, etc. Okay, till Siemens was, the engineer Siemens, another German gentleman, he was honored by a unit in the electrical systems. Also we can say that the potential difference is proportional to the current. This is the familiar form. So I can write this as V is equal to Ri, where the constant of proportionality of the system, which does not depend upon I and which does not depend upon V, like in all things. So this is called resistance, and its unit is Ohm, symbol is Ohm. Okay. Omicron or omega. Okay. In Greece. So of course, with the systems approach, here also I say that the capital G is not a function of V, is not a function of I, and is therefore a function of the system. Okay. Now let us see. Let us have a tabulation of the values of voltage and the current. Okay. And when I plot this, I get a straight line graph over here. I is proportional to V, and the slope will become equal to capital G. Science. Otherwise, V is proportional to I. V is proportional to, here I must have written I, and in that case V is equal to Ri, and the slope becomes equal to R, like we have been doing before. Of course, from this relation I can write G is equal to I upon V, okay, amperes upon volts, and this is called 1 upon R. Similarly, R is equal to V upon I, R is equal to V upon I, and this I can write as equal to 1 over G. So that means G and R, they are the reciprocal of each other, which I am expressing in the form of a graph, G on the y-axis and R on the x-axis, and it will turn out to be equal to GR is equal to 1. That means the area formed will be constant for all sets of values of G1 R1, G2 R2, G3 R3, etc. etc. Okay. So this finishes off with the presentation and the understanding of Ohm's law. Well, later on, Ohm, he changed the length of the conductor. He also changed the area of cross section of the conductor, made them variables one by one, and then he found that, look here, the value of R that I obtained by V upon I, okay, V upon I, calculating V upon I, the value of R is proportional to L and is also proportional to 1 upon A. Okay, so there are two variables L and A, and R is proportional to L, R is proportional to 1 upon A. So for mathematical consistency, as I told you in the multiple systems, variable system, R is proportional to L upon A. So what will happen? Therefore R is equal to some constant times L upon A. R is equal to some constant times L upon A. This constant will not be a function of L and will not be a function of A. Okay. Also not a function of R, because R is also variable. Then the question is, what will be a function of? It will be a function of the system. Those things which have not been defined. L and A are defined variables of this system, and other things are in the system. The system consists of a particular material. The system consists of a temperature. The system may even consist of a pressure, etc., etc. But the major things are temperature and the composition of the material that is there. This material is supposed to be isotropic. It is supposed to be uniformly inhabited by the atoms or molecules of which comprise this particular material. Okay, area of cross section is everywhere the same, right? L is changed, A is changed. Now this is called resistivity. This is called resistivity, which is the reciprocal of, I'll talk to you about that, what is known as conductivity sigma. Okay, conductivity sigma. I'll give you the units also, but before that I just plot it in terms of the system. R is proportional to L, and I'll get a straight line like that. R is proportional to 1 upon A, and therefore if I plot against A, I'll get a graph like this. If I plot against 1 upon A, I'll get a graph just like this. Okay. And like this case, rho and sigma, they are opposite to each other, and this is, I'll get rho into sigma again just like that. The area will be equal to 1 without any unit, etc. Okay. So for the first time, and before also we have obtained in the case of heat, etc. Okay, I have got two terms, resistivity and conductivity. Okay. Now in physics, anytime you find a term like that, EVT, TVT, ET, VT, in the end, okay, while we are doing it in English, EVT, TVT, ET, VT, okay, that is always the property of the material. But if we have ands, tans, etc., that is the property of the device. The device, resistance, conductance, capacitance, etc., etc. Inductance, etc. Now, I wind it up here. The unit of resistivity is ohm meter. Okay? Ohm and L upon L square, so this will become meter. Ohm meter. And 1 upon that, ohm meter will become equal to Siemens per meter. Not very long back, and class 9th, 10th, etc., when they might have introduced something like this, we talked about the specific resistance, specific conductance. Okay, I don't subscribe to that. The youth today, the students today, they are intelligent enough, they are very sharp, and they can talk about terms like resistivity, conductivity, okay, etc. Okay, so I wind up here, I leave you here, and I expect from you to read through all these things when you come back, when I tell you how come the resistance or conductance is obtained from the theory which is similar to the kinetic theory of gases, that is the free electron theory of metals. I'll do that and then tell you more about resistance, combinations, etc. Thank you very much. I've enjoyed. Hope that you have enjoyed. Ask your questions if you have any.